right, so our project title is titled MEKHOS, which is a Greek root for the word machine, meaning cure or remedy. And it is our interest to speculate and turn the industrial aesthetic and conventional modes of waste production on its head through investigations of advanced structural optimization and robotically manufactured techniques.
So with that said, we are looking specifically at electronic or e-waste, which refers to any electronic waste ranging from small home appliances to intricate computer parts. In 2016, over 45 million metric tons of e-waste was generated, and though the composition of this waste varies by definition, a majority of this waste was composed of ferrous metals, plastics, and glass, respectively. Roughly 80% of this waste is exported by the largest producers, like the United States and European countries. And it's generally exported to areas of India, parts of Central Africa, and to Southeast Asia. And it has had a profound impact on these areas and exposed millions of people to toxic fumes, polluted streams and natural wildlife habitat, and has left large swaths of material waste to decompose in the open. And in the next 5 years, the global generation of e-waste is expected to grow by 4 to 5%. Slide. The other side of the issue, of course, is that the motivation of countries who import these materials, despite drawbacks, is that the raw materials in e-waste contain immense value. In 2016, nearly $65 billion worth of e-waste was generated. And in the United States alone, Americans threw away over $61 million of gold and silver. And as a result, finding ways to take advantage of these materials has been a race in and of itself. And since 2004, there has been a surge in patent applications for the recycling process of e-waste, specifically in Southeast Asia. And actually, in the center of this image, some of the technologies here, this is a sample of a machine that can take coarse regrind and turn it into useful plastic pellets for manufacturing. So some waste can be recycled. The capability to recycle e-waste allows it to be reintegrated into the manufacturing process, creating a virtually circular flow of materials with far less environmental impact. And of course, this project was conceived with Shapeways in mind, which, as you know, is a 3D printing and manufacturing company based in New York. To date, they have shipped over 10 million printed parts to 130 countries, and they can print in over 50 unique materials ranging from nylon-based plastics to precious metals and advanced composites. And in New York City, they have 2 locations, one in Manhattan, which is more of their office facility, and one in Long Island City, which is a predominantly industrial area. And in the map to the lower left, surrounding them, there are many recycling centers. Highlighted in yellow are general recycling centers, and highlighted in green is the nearest e-waste recycling center, and is less than a 6-minute drive from their site, so it's extremely close. And essentially what we're kind of driving at is that the ballooning volume of e-waste produced in close proximity of an e-waste recycling facility to the Shapeways factory presents a unique opportunity. By utilizing this relationship, they would gain a reliable stream of raw materials. They would be able to vastly reduce the amount of e-waste exported to foreign sites, not just in terms of lowering the amount of environmental damage done, but also to lower the amount of valuable materials that are being exported. And just for reference, there isn't great data on the material volume that Shapeways goes through, but they're currently shipping roughly 180,000 printed parts per month at an absolute minimum cost of $5.35 per part with their cheapest plastic. And that is immediately almost $1 million in value. And of course, they're printing much more complex, much larger parts with much more expensive materials. So this would give them an opportunity to massively reduce their bottom line. So essentially, they have the opportunity not only to bolster the logistics of the business model, but also to incorporate this virtually circular process into the re-envisioning of their facility and their brand identity. And we are re-envisioning a new Shapeways factory that is not only an iconographic new facility for Shapeways, but also a mission-critical project aiming to maximize the potential of recycling and advanced fabrication working harmoniously.
Then when these issues of the byproducts of the Anthropocene and the electronic industry intersect with our site, and what architectural complications does that arise? You can see also what other issues of what devices and programs can come about of such a raw process. And so looking at our site, what is initially a rough brownfield site as a deposition location for piles of waste of new materials, granulated PCB board polymers, metallic pellets, all delivered through conventional means such as trucks and diggers, now become a canvas performer on which our projects can form. The mechanical equipment for delivering, transporting, and processing the three raw materials of e-waste now situate themselves for optimum workflow, ready for the architecture and program to form around it. The primary prefabricated pieces of the building are then craned into place, covering programmatic functions of both public and manufacturing spaces in the form of roofs and shells. After 3D printers form and join these roofs and shells together using the very materials that were on site, the building begins to shine through night, expressing the translucent qualities of the light inherent in the green PCB plastic, while reflecting the light of the day in the metallic compounds as a one intrinsic matter. And inside, we can see the floor plans, which Zach is going to continue talking about.
Yes. Okay. So starting at the, is there something in the top of the screen?
No.
Oh. Anyway. Starting at the bottom or south end of the slide, you can see an inlet that leads toward the primary public entrance of the building, denoted by A1, flanked on both sides by these large material piles. And upon entering, there are gallery and showroom spaces at these circulation cores, marked by 2. And at these points, the user has essentially a view into the entire manufacturing space on the ground level. And further north on the site, the manufacturing space in the center gives way to the primary material processing area, in which the deposited piles are refined into ready-to-use material. And starting in the center of this plant, roughly where the ones are, the primary public circulation feeds to these areas where the manufacturing space is again on full display, and it continues to a promenade that wraps the north end of the factory above the material processing area. And on the left side of this upper level, there is an artist in residence incubation space, and on the right side there's the more private administrative area.
So zooming out, we can see that in the roof plan that the way this building sort of materialistically performs relates directly to the piles and materials that are deposited on the site. As you can see through the different colorations of the materials, the building also responds to that directly. And there's also a intrinsic representation of not only surface structural seams, but also glazing at the top, sort of bluish areas of the membrane covering towards the left side. And at night, the project isn't imposing as it stands out, but it does respond to the surrounding conventional factory buildings with a critical sort of response that proves a statement for the Shapeways factory that it can convert waste into progressive architecture. And here's a close-up of that elevation during the day, where the mechanical equipment and the machines still in place are now integrated fully with the building and the materials that are used to print over. And coming around the front corner, or the back corner, we can see facing towards the city that the membrane materials, which are also printed using the same piles of e-waste byproducts, then begin to thin out This part of the building is the thinnest and thus the lightest, showing both the multiple functions and abilities of printing with this material.
So this is a bit of a closer look at the structural material development. Like the other groups, we looked at Luigi Neri as a precedent, and we found his turn exhibition hall to be interesting because of the way that it distributes the roof loads to the very articulated columns and the thinness achieved by them. And from here we look to reinterpret these elements and use them as a point of departure to develop new aesthetic typologies for our own project. And we started by kind of creating somewhat simplistic variations of these column configurations and using topological structural optimization to kind of guide us in developing a new interpretation of these elements. Next slide. And as you can see, this element is beginning to develop a combination of column, beam, and slab working together in a single element. And in this section, you can see that this element is beginning to form the overall structure of the building, and in addition, it's beginning to articulate itself into the slabs and the walls. And on the lower level, it is dividing the manufacturing space with the exhibition spaces, and on the upper level, these cores are linking public spaces.
When we zoom in, the trunk shows how the structures develop into branches on the top, and how the structure divides the exhibition and the manufacturing space. Next. This is a gallery entrance space exhibit shipways work. The mezzanines above connect to the artist resident on the second floor, and on the canopy, fully 3D printed structure envelope was designed for daylight and natural ventilation.
So the 3D printing process basically reflects itself into the tectonic and the expression of the structural columns that you see here, whereby the same material, possibly with speculation of dual extruders or triple extruders, the material can switch while it is printing. And as you can see, as the building sort of ventures further out towards the back of the site, the material starts to thin out and become really strenuous and thin. The material at the roof begins to morph into different colors as it responds to the different materials that are used to print it, and also opens up to more qualities of light where it thins out. Looking closer into that bottom manufacturing space at the center, we can see then this intrinsic metallic quality of the structural printing, then integrating directly with the green plastic, both of which are also of the e-waste byproduct itself. And you can see the truss system on the roof, as well as lighting and equipment below that. This still does function as an industrial manufacturing space with artist residence on the second floor. So the bifurcating here shows that where the material is behind us, it is delivered to the side, the two belts on the side flanking us to the left and right to the artist residence area on the second floor, while it can also be transported directly to the front for the robots to process, package, and deliver out to other customers who would then reuse these pellets directly. And so looking at the basic process of which our semester and how basically our geometry came to be, we first initially investigated 3D printing techniques on three-dimensional surfaces and experimented with different formworks and looked at how this type of aesthetic and as well as additive manufacturing construction technology allows us to create different spaces within this this type of form itself. As you can see, some of these initial tests are not so different from the initial interior renders that you saw previously. This is a sample of one of our quick tests using basic clay and sand as formwork. And this was the textured simulation that we ran on that file. Just to prove a point, initially, as you saw in the chunk earlier, our basic premise was that the building would be printed from the columns first as their strongest points, and then from that point, departure off to print and sort of branch out and basically print the rest of the building. And so this simulation that we ran with the swarm simulation shows that from the basic points of structural column positioning, the building can then be printed progressively outwards as a sequence. And here, this is just a speculation of how that printing process could have been, with sand as well and piles as formwork. And this sort of technical drawing shows the composition of one of these shells and the column transitions. So it's kind of basically it's a column shell hybrid. And so this type of morphology that's kind of developed upon using 3D print geometry as well as the techniques sort of also show in this drawing that the robotic arm can reach multiple radii to print this. And as you can see, our mock-up is in Pennovation. You can go visit. But I'm just kidding, it's a rendering, it's not actually there. But at least it shows the speculation of how this thing situates itself if it was at scale.
We want to show the material dynamics of the building in this overall front elevation. The building is not only mass, but also the piles and materials, and the activities surrounding it. As you can see, dumping, depositing, extraction, and reusing these materials. So the building is under changing constantly. Next. When we zoom in, you can see the canopy nests between the piles, and the geometry of canopy is designed to fit snugly with these piles. So it emphasizes the building is in structure, and the raw materials are also one part of the building. From our view, we can regard the architecture as a crystallization of these raw materials. And this process is taking place either throughout the life of building or through the reusing of waste materials. Next. We want to show the structure grain in this super close-up view of canopy. There are 3D printed structure envelope inside the seals and structure strips on the branches, and both of them follow the same structure grain. Next. As a 3D printed building, we can see the ceiling is composed by variable geometries. As we know, complexity is free according to the 3D printing principles. And on the other hand, multi-material 3D printing could help us to control the spatial distribution of different materials. So we try to integrate all of those variable geometries and materials into one reflected ceiling. Next. When we zoom in, as you can see, on the center, it gets a setting of circuit board, which is inspired from e-waste, some kind of very industrial aesthetic. And on the other hand, these structure strips on the both sides look like meat tendons, some kind of very biological aesthetic. And we integrate these two totally different features and aesthetic into one thing, take fully advantage of 3D printing techniques. Next. Yeah, I think this is our last image. Just another zoom-in view of our reflect ceiling plane. That's it. Thank you.
Thank you.
Maybe it's look.